For this problem, they're better. So one example of a binary search tree looks like this. And it's a binary tree. You have a node, and we call it x. Each of the nodes has a key of x. So 30 is the key for this node, 17 for that one, etc. Unlike in a heap, your data structure is a little more complicated. The heap is simply an array, and you happen to visualize it as a tree. The binary search tree is actually a tree that has pointers, unlike a heap. So it's a more complicated data structure. You need a few more bytes for every node of the binary search tree, as opposed to the heap, which is simply an array element. And the pointers are parent of x. I haven't bothered showing the arrows here, because you could be going upwards or backwards. And you can imagine that you actually have a parent pointer that goes up this way, and you have a child pointer that goes this way. So there's really a potentially 3 pointers for each node: the parent, the left child, and the right child. So pretty straightforward. That's the data structure in terms of what it needs to have so you can operate on it. And there's an invariant for a BST. What makes a BST is that you have an ordering of the key values that satisfy the invariant that for all nodes x, if y is in the left subtree of x, we have, if it's in the left subtree, then key of y is less than or equal to key of x. And if y is in the right subtree, we have key of y greater than or equal to key of x. So we are talking about trees here, subtrees here, everything underneath, and that's the stronger part of the invariant in a BST, versus in the heap, we were just talking about the children. And so if you look at this BST, it is a BST, because if I look to the right, I only see, from the root, I only see values that are greater than 30. And if I look to the left, in the entire subtree, all the way down, I only see values that are less than 30. And that has to be true for any intermediate node in the tree. And it's the only other non-trivial node here is 17. And you see that 14 is less than 17, and 20 is greater than 17. OK? So that's the BST. That's the data structure. This is the invariant. So let's look at why BSTs are a possibility for solving our runway reservation problem. And what I'll do is I'll do the insert. So let's start with a nil set of elements, or null set of elements, R. And let's start inserting. So I insert 49, and all I do is make a node that has a key value of 49. Right? This one is easy. I next insert 79. And what happens here is I have to look at 49, and I compare 79 to 49. And because 79 is greater than 49, I go to the right, and I attach 79 to the right child of 49. Then I want to insert 46. And when I want to insert 46, I look at this. I compare 49 and 46. 46 is less, so I go to the left side. and I put 46 in there. Next, let's say I want to insert 41. So far, I haven't really talked about the k-minute checks, and you can imagine that they're being done. I'll show you exactly, or talk about exactly how they're done in a second. It's not that hard, but let me go ahead and do one more. For 41, 41 is less than 49, so I go left. 41 is less than 46, so I go left and attach it to the left child. All right, so that's what I have right now. Now let's talk about the k-minute check, and it's good to talk about the k-minute check when there's actually a violation. And let's assume that k equals 3 here. And so same thing here. You're essentially doing binary search here, okay? And you're doing the checks as you're doing the binary search. So what you're going to be doing is you're going to check that you're going to compare 42 with 49 with the k-minute check, and you realize they're 7 apart, so that's okay. And 42 is less than 49, so you go left. And then you compare 42 with 46, and again, it's less than 46, but it's k away, 3 away, more than 3 away from 46, so that's cool, and you go left. And then you get to 41, and you compare 42 with 41. In this case, it's greater, but it's not k more than it. And so that means that if you didn't have the check, you would be putting 42 in here. But because you have the check, you fail, and you say, look, I mean, this violates the safety property, violates the check I need to do, and therefore I'm not going to reserve a request for you. All right? So what's happened here is it's basically a sorted array, except that you've added a bunch of pointers associated with the tree. And so it's somewhere between a sorted list and a sorted array. And it does exactly the right thing with respect to being able to insert. Once you've found the place to insert, it's merely attaching this particular new node with its appropriate key to the pointer. All right? So what's happened here is that if h is the height of the tree, then insertion with or without the check is done in order h time. Okay? And that's what BSTs are good for. People buy that? Any questions about how the k-minute check proceeded? Yeah, question.
So what's it called, the what check?
The k-minute check. Sorry, the k was 3 minutes k. I had this thing over here. Add t to the set r if no other landings are scheduled within k minutes. So k was just a number. I wanted it to be a parameter because it doesn't matter what k is, as long as you know what it is. When you do the binary search, you can add that in to an argument to your insert and do the check. Okay? So in this case, I set k to be 3 out here, and I was doing a check to see that there weren't any elements in the BST already, or any nodes that had keys that were within 3 minutes, because I fixed k to be 3, to the